Good morning, everyone. So today, let's continue our discussion on using Ampere's law to solve finding the B field for different geometries of different current carrying wires. Previously, at the end of last class, we did a long wire with a current flowing this way, right? This is the example we did. And in this example, we showed that B is mu naught I over 2 pi s. S is how far you're away from your wire. This is S. And B is in the phi hat direction. Okay. And you can see that we find out it's in the phi hat direction using different claims. I don't know if you still remember. We said there shouldn't be an S hat direction because that will violate diagonal magnetic monopoles. And since Biot-Savart says B is perpendicular to the current and that current in the Z, so B should not be in the Z direction. So the only possible direction is phi hat. Okay, and that can be shown by following the right-hand rule, right? Your thumb is pointing in the direction of the flowing of the current, and your forefingers points in the direction of your magnetic field. Now let's continue to solve a problem that's very similar to that, but it's a thick wire. So instead of current flowing through just a long thin wire, we have this current flowing with a thick wire with radius A, and it is flowing in the Z direction. Okay, and this is, we call it current density J. We have uniform current density J, that is J naught in the Z direction for everywhere inside the wire. Outside, of course, you don't have your current and zero current density. Okay, so the only difference is now the wire is thick. So let's do the Ampere's law. So we'll draw our Ampere loop, just like what we argued before. Again, we think our current magnetic field should be in the phi hat direction. So I'm going to draw a loop that's like this, right? Center around the origin with a radius S from the center. So if, just like when we do Gauss's law, right? We do a Gaussian surface. Instead of Gaussian surface, do Ampere's loop. Here we do outside. Let's do the outside of the wire. At S is larger than A. So if you're outside, B dl equals mu naught I. B dl is B times 2 pi S. What is the current? Current is you are enclosing all the current. So current is J times what quantity? How do we get the current? Current is density times area, very good. So the cross section of the area is pi A squared. Okay, so you can find B is mu naught J naught pi A squared over 2 pi S, which is mu naught J naught A squared over 2S, and it's in the phi hat direction. Okay, now if you want to find B inside, so let's draw another Ampere's loop. I'm going to draw a smaller Ampere loop, again at a distance S away from the origin. The same process, mu naught I enclosed. Okay, B 2 pi S and mu naught I enclosed. Now the current enclosed is J times what quantity? So what is the current enclosed if I draw my Ampere loop inside? What do you guys think?
Would the current enclosed be 0? So it's on the surface, or?
So this is a volume density, which means everywhere throughout, throughout this volume, you have current flowing all the way through. I get a chat. Hoying says it's pi S squared. Very good. So instead of enclosing the entire cross section, right, enclosing everything, now you're just enclosing part of that. So this part of that is pi s squared instead of all the area is pi a squared. Okay, so it's pi s squared. So you can see it's very similar to the Gauss's law example we did with a solid sphere. Inside, your E field increasing. As you go outside, it behaves like a point charge. Right? This is the same. Outside, it behaves just like a long wire. Now, but inside, you can see that the B field is increasing with S. So it's mu naught J naught S over 2 in the phi hat direction. So this is inside, this is the outside. Okay, I want you to recall the comparison with Gauss's law for a solid sphere. So it's very similar to how we did that. All right. Okay, so the second example I want to do is this infinite sheet. Remember we did this using Biot-Savart and it was quite complicated, right? We had the y hat, a zy hat, y z hat integral, and one of the integration is 0. Remember that very complicated calculation. So for a surface current, we have a symmetry and we can solve this much easier using Ampere's law. Right? Instead of doing the Biot-Savart, we can do this using Ampere's law. So which Ampere loop that you would draw if you want to calculate the B field above or below the surface? So which of these loops that you think will be useful, A or B? So A is really just perpendicular to the sheet, but is above the sheet. B is cutting across the sheet, perpendicular to the sheet. C is a plane that's parallel to the sheet. And D is a circular loop cutting across the surface sheet. Okay, so I'm gonna go ahead and let you vote on this. If you still remember from our previous discussion in which direction the B field is, then this should be fairly straightforward. Okay, all right, 10 more seconds. Okay, any last minute vote? All right, so let's take a look. I'm gonna we'll go ahead and end this. This is our results. Yes, to find B, we know that we need to draw a loop that you need enclosed instead of, oh, sorry, not enclosed current, it's the current flowing through the loop, right? So your loop should cut across the source. So obviously, B and D will be useful in that regard. Now the question would be, what kind of shape do we draw? So in order to figure out what shape do we draw, we need to know in what direction is B. So do you still remember for this kind of distribution, what direction is our B field? Is our B field, if you were to draw D, indicating our B field wraps around in the phi hat direction. If we draw B, indicating our B field is parallel to the top and bottom leg of the loop. So which one do you think it is? So if I do right hand rule, saying my current flowing this way out of the page, and my B wraps around in the circle. Is that correct?
Yeah.
Instead of, but I have many currents. So if I have one current going this way, another going that way, how do these add up? Do they add up, becoming what kind of circle? Obviously, you have many. If I treat, this is not an individual wire, but one wire, you have current going in the phi hat. I have many individual wires becoming an infinite sheet. So how do these different circles add up?
Would they add up so that your B field would be pointing perpendicular to the top and bottom of the sheet?
Yeah, they will add up. So it's not in the circle anymore. It will be in the fixed direction. So I'll go quickly review this, what we did. We argued previously, let's take one of these surface current, for example, this one. We take one of them, and if you draw a circle like that, right? And you take another one and you draw a contribution, just a contribution for that. And it looks like this. Okay. And you can see that the Z direction cancels, okay? Leaving only the component that is parallel to the sheet. Here is pointing to the left, negative y hat. Here is pointing to the right, positive y hat. So it becomes actually above the sheet is to the left, below the sheet is to the right. So it's best to choose B, because on top, right, you want your B field to be parallel to DL, and on the bottom, you want your B to be also parallel to DL, okay? So be very careful. This is not a wraps around, because you have many of these contributions and giving you only the Y direction. And this can also be done, if you recall. We did this, we was using Biot-Savart, and we look at the integral. One of the integral cancels out, leaving only the Y hat direction, okay? All right, so now establish B is in the Y hat direction. B is in the negative Y hat at above, positive Y hat below. So this is the direction of B. So therefore we choose the Ampere loop indicated by B, choice B, and we do our integral, see what this becomes. Mu naught I through, sorry, not enclosed, but through. So BDL becomes B times L here and B times L here, because you have the top and bottom leg, right? So 2BL. Sorry, I don't know why the screen went away. 1 second. I need to replug in, so hopefully that works. Okay, all right, sorry about that. Okay, so this is BL, 2BL. On the right-hand side, you have mu naught. And again, this is a surface current. Surface current is surface current density times L perpendicular is I. Still recall that? So here, the L perpendicular would just be the loop, the length of the loop that you were looking at. Okay, so and then we choose Ampere loop to be however long that you want, and it doesn't really matter. This is very much similar to when we do Gauss's law. The length cancels out. We do our B to be 1/2 mu naught K. Okay, so it's a constant, which is in the negative Y hat above the plane, and there's a positive Y hat below the plane. Okay, I want you to also draw the analogy with a surface, large infinite sheet of the surface, charged surface, with E is sigma over 2 epsilon naught Z hat above -2 epsilon naught z hat below. Very similar to that, okay? All right, so that is again an example of using Ampere's law to solve a surface current density. So the next example is a solenoid. This is what we're very familiar with for a long solenoid with current I. So I kind of wraps around in the phi hat direction, and this one has a radius R, radius A, and the turn density is N. So this is tells us how tight you're wrapping around your solenoid, which is how many turns per unit length. You have 1,000 turns per 20 centimeters or something. It tells you how much you're putting all the wires together. So again, this one we can use Ampere's law to solve this. First of all, we have to in order to know which Ampere's loop to draw, we need to figure out what direction do you think B is. Okay, so remember I know that you already know what direction B is from the previous knowledge, but let's try to make these claims from scratch. So B, again, we have this cylindrical symmetry. So first of all, I claim B does not have a phi hat component, very much like what we did before, because if you do have an S component, it radiates away from the center. That's an S component, right? The radial component. If you do have that component, that will violate the no magnetic monopole. It will violate that Maxwell equation. So we cannot have an S component. Can B be in the phi hat? So here our current is in the phi hat. So B, using Biot-Savart, B is perpendicular to the current. So current is in the phi hat, so B should not be in the phi hat. Now it looks like it will be reasonable to claim that B is in the z hat direction, perpendicular upwards. Okay. So I'm going to say B is in the z hat direction and has a dependence with respect to radial distance. Again, so here is our argument about its direction. You can have a separate argument about its dependence, S, phi, and z. The dependence one is quick to do because the solenoid is long. So if you move yourself up and down, you shouldn't see any difference in your B because your physical source is still look exactly the same to you, right? Doesn't really matter where you move up and down. So it shouldn't depend on Z. And phi is you walk around, you turn your head around in the phi hat direction. Do you see a change in B? Again, you have a symmetric source that is in symmetry, has symmetry in phi hat. So if you move from here to here to here, you're looking at the same physical source, and that should not change your B field because it's still very much the same setup, right? So phi should not have a dependence. It's only possible to have S dependence. So after making those arguments, we say, okay, B is in the Z direction, and B might depend on S. So how do we draw an Ampere's loop to calculate the B field inside the solenoid? We will do that for the outside again, but we can do either inside or outside first. But first of all, we have to decide what shape of the loop that we draw, right? So what kind of a shape of the loop that you want to draw? Do we want to draw a circle or do we want to draw a rectangle?
Rectangle like the one before?
Yeah, very good. Okay, so I'm going to draw a rectangle and I'm going to calculate my B outside first. Okay, we'll do the inside next. So we're going to draw an Ampere's loop outside. Because B is in the Z hat, so I'm choosing my loop to be oriented in that direction. So you can do a loop kind of like this. It doesn't really matter. I'm sorry. Doesn't really matter which way you're going. So I'm just randomly choosing a B out. So if there is a B outside, I don't know. At first, we don't know the results from before. Pretend we didn't know anything. So it's reasonable to argue, okay, I might have a B outside. So if I do have a B, I will have a B here in the Z direction that is at a location S1 away from the center. And I may have a B outside at a location at S2 away from the center, though that is goes in the Z direction, right? I'm going to choose my loop in this way. Okay, let's see what we'll get if we apply Ampere's law.
I had a question. Isn't the B field down in the negative Z direction using the right-hand rule? I'm getting, where am I off?
So your current is flowing this way, right? Wraps around this way. So B will be up, right?
Isn't it you point your thumb in the direction of the current and it's the fingers?
Oh, if you have a long wire, it's very yes. So for a right-hand rule, there are two different ways to use it. When your current is straight,
Okay.
then you do your thumb. But when your current wraps around, you switch your thumb and four fingers, and your four fingers becomes a current. Yes, thank you for pointing it out because I
Thank you.
forgot to mention it, and it is confusing. So if your current, whichever your current is straight, then you use your straight finger. If your current wraps around, you use your four fingers. Okay, so the current is wrapping around in the counterclockwise direction, so the thumb points in the B direction, so it's upward. So again, I'm going to use this, okay, Ampere's law. So I'm going to use Ampere's law for a loop that I draw outside. And you can see that if this is L, this is L, I'm going to do the line integral. The line integral here is B S1 times L. The line integral here is negative because my loop goes down, but my B is still up. So negative B at another location times the same length L. And is there any current through this loop outside? There's no current, right? Current is not through this loop. There's no current. So 0 on the right-hand side. Just like Gauss's law, if you're not enclosing any charge, there's 0, right? If you're not enclosing, if you don't have any current through, it's 0. So I get BS1 is equal to BS2. It looks like my argument is the B field outside at different locations are the same, which is a constant. So now the second question is, what is this constant? Is it a non-zero constant? Then you have to invoke something else. We can call this boundary conditions. From in limits, I do know what B has to be. So I argue, well, if B is a constant all the way here, now I can draw my loop. So if this is my solenoid, I can draw a loop here, I can draw a loop here, I can draw a loop here, I can draw a loop all the way to infinity, and they're all constants. All of them will give me B is here, the same as here, as here, as here, as here, as here, as my infinity. So they should equal to B at infinity. And what is B field at infinity?
Zero.
It is 0, yes, yes, very good, it is 0. It is an experimental fact because you can always try to measure your B super far away from a solenoid, get 0. And also from Biot-Savart, B drops as 1 over R squared. So R goes infinity, U goes to 0. And or just this has to be physically make sense, right? If you go super far away, your away from your source, makes sense physically for your field to go to 0. So actually, from Ampere's law, we got the B outside of a solenoid is 0. This is something that I know you have already learned in previous courses. Okay. All right, so that's useful, but it's not directly something we want to calculate. We want to find B inside the solenoid. And it looks like now we have to draw another Ampere's loop. So this is the first loop we draw. Using that loop, we can argue B outside is 0. That's very nice, but I want to know B inside. So I'm going to draw another loop too, which cutting across my source. I need to have my source through it, right? So I'm going to draw loop 2. So let's use loop 2 to find our B field. Okay.
Dr. Ryan, I has a question.
Yeah, go ahead.
So when I'm confused why the B field doesn't increase in the Z direction, because doesn't your mu naught depend on the number of turns which you create?
Mu naught, you said?
Yeah, I was saying I was going to say that mu naught is equal to n I something, I forget what the full formula is. So as we're increasing in the Z direction, aren't we adding more n's or more turns to our current, which scales our magnetic field?
I think you were quoting the final expression for B inside the solenoid. As yes, it's mu naught n times I. Mu naught is just a constant. It's at 4 pi times 10 to the negative 7. You still remember that? It's the magnetic constant. So mu naught is just a constant. Doesn't it's you don't it doesn't depend on the turn.
Okay.
The B field does depend on the turn. So the more you wrap around, the more of a B field you'll get. But we're talking about when you already wrapped around, it's uniform across the Z. So no matter if you're looking at here or looking at here or looking here, it's all the same solenoid to you physically, right? To your eye.
Okay, thank you.
We are still assuming an ideal solenoid. It's still the length is much longer than its width. So we call it an infinite solenoid. Obviously, it's like the Gauss's law when it's infinite long, a same rod or something, right? If it's too short, then obviously that would not work.
Okay, thank you, Dr. Aaron.
No problem. Okay, so for inside, we are going to draw loop 2 that cutting across your source with current running through it. You can see the current, all of these are current through it, right? So let's do the Ampere's law, mu naught I through. And again, looking at, okay, my B field outside, I already said B outside is 0. So there is no B dot DL on this leg. There's only going to be a B dot into DL on this leg. Oh, just to make that my integral to be positive, I'm going to make my loop to go this way. So I don't have a negative sign coming from this B dot into DL. This leg is 0. This leg is BL. Okay, so it's just one BL. Based upon the B is outside, is 0 outside from the previous step. So how many current is running through? Okay, so you can see that my current is going to be, each of them is I, and you have to think about, okay, how many turns? So how many turns? I have n turns per unit length. So let's say 20 turns per meter or per centimeter, and that's 100 centimeters for now. So the total number of turns is n times L. So this is total number of turns. Okay, so you can see that L still cancels out, and B is mu naught n times I, which is the B field inside the solenoid in the Z direction. And you can see this is a constant. Once you have a fixed current and fixed number of turns, inside it's a constant. Meaning that as long as you're inside the solenoid, you go whichever way you go, it's still the same value, which is mu naught n times I. So that's the result for a solenoid. So overall, we conclude B is mu naught n I Z hat for inside, okay, which is 0 for outside. So this is a solenoid. Okay, so we have draw the 2 loops, and we pretty much solved this problem. So if I ask you, what if you draw a loop 3 inside? Let's say you don't have a particular order of knowing which loop to draw first. First of all, you just draw a loop 3 and you apply Ampere's law on it. What kind of results do you think you will get from drawing a loop 3? I think based on what we did previously, you should be able to answer this question. So I'm going to go ahead and let you vote on this. Okay. Imagine you draw a loop 3 and you apply Ampere's law, what conclusion would you get? Knowing that even if loop 3 will not be very useful to find the exact expression for B, it should not give you any conflicting results than what is correct, right? So even if loop 3 is not useful, it shouldn't give you something that is wrong. Okay, all right, 10 more seconds. If you haven't voted already, 10 more seconds. Okay, let's take a look at your results. This is what we have. Majority voted for A, the B field inside is 0, and the next one is, it doesn't tell us anything about the B. And C is something else. So is it possible we get B field inside is 0? We just calculated what B would be for a solenoid. What is B inside a solenoid? Is a non-zero number. So if you draw a different loop, do you think you would have got the conclusion that B inside is 0?
Well, in my head, it doesn't make sense why we would have two contradicting answers.
Right, it shouldn't contradict. So let's see what happens when we apply the Ampere's loop for the loop 3. It shouldn't give us anything wrong. At most, it gives something not useful. Okay, so let's come to choose our loop to be like this. And this is at B at S1. This is B at S2. We don't really know which one. Okay, so we apply Ampere's law is BS1 times the total length L. And if you say, let's see which way it's going this way, your B is going this way. So this is positive, right? This dot product is positive. The top leg, the dot product is 0 because L is to the left, B is to the right. So the top leg give a contribution BS2 times L. The two other legs, there's no cross product, a dot product because they're perpendicular. So these two are mu naught I through, and you're right, the I through is 0. No current is through. So I think a lot of you choose this because you see that I through is 0. That doesn't necessarily mean B is 0. Because if you look at this equation, all it tells you is BS1 is equal to BS2. Give you a 0 line, a line product, a line integration. The circulation is 0. Okay, so what does this really tell us? It's not A. It doesn't tell us nothing, tells something. So it tells us something else. What is that something else? What does it tell us? That B inside a solenoid is constant. Very good. That is what we derived. It's not completely useless. We know it's constant. And if you do not want to know what that constant is, you have to choose loop 2 and you find this constant, right? This is the constant. Okay, so you can see each of the loop has its use. A lot of times we really just jump to calculate our results and be done. But I also want you to see the nuance behind all of this reasoning, that you can still get some useful information out of week 1 and 3 of the setup. Okay, all right, this is from your pre-lecture questions, pre-flight questions. So now let's look at them one by one. Pick a sketch showing the B field lines that violate one of the Maxwell equations. And I think you know which Maxwell equations I'm talking about. Which one of these violates del dot B equals 0? And which one? You can simply just go ahead and say the answer or type it. Which one of these clearly violates the no magnetic monopole law? Yeah, I see a lot of votes for D. Very good. Excellent. D is wrong, because that indicates definitely radiating out from the inside, giving you a positive divergence, right? Have a positive non-zero divergence, which is a positive. You also have a positive flux, and that's wrong. Okay, so but everything else is possible. So everything else, let's find the physical setup that give us all the other possible fields. Let's look at A. What kind of field would produce, what kind of a current distribution would produce a magnetic field that looks like A?
The plane we were talking about earlier would make A.
Yes, very good. The plane, if you have a surface current density with, now I believe this has to be in this way, the plane with a K pointing into the page, that will give us A. Excellent, very good. Okay, what kind of source will produce B? B looks like it's in one direction and is uniform. Have we talked about something like this just now? A solenoid, very good. B give us, it's a solenoid. It must be wrapped around, the current is wrapping around in this direction, okay? Like that, like that. Okay, solenoid. And what about C? Okay, Benjamin says a wire loop, very good. So if you have a current loop, and if you still recall, the magnetic field lines coming out of the loop is kind of like this, right? Kind of like this. E is like this. Yes, that looks like it will give us C. So it's a loop of current. And what kind of distribution will produce E? E still looks like B is wrapping around in the negative phi hat. So one might argue, what if we have a infinite long wire that is going in the negative Z direction? Would that work? Would that work?
I don't think it'll work, because looking at the vectors as we move farther away, away from the, I don't know, radius of your B field, it increases, which doesn't make any sense.
Yes, right. So the only difference from a wire is as you go increasing your radius, your B actually increases. So, okay, so a thin wire doesn't work. Have we talked about any example just today that show us a B field increasing as you increasing your distance?
Inside the thick wire?
Inside a thick wire, very good. So we can have a very thick wire. So instead of one eye, we can have a thick wire with current going this way, then inside, yes, your B must be going bigger and bigger. B is proportionally increasing with S that's in the phi hat direction. Very good. So we found all the physical examples that give us all the other possible B situation except D. D is not possible. All right, so I'm going to summarize everything that can be used, be solved by Ampere's law. If you see infinite current carrying wire, Ampere's law. You see a thick wire, is also, we can use Ampere's law. When oftentimes you will say it's still infinite long, which means the length is much larger than the radius, so it's still a good approximation. You see a solenoid, obviously we use Ampere's law. And there's something else that is very similar to a solenoid. So instead of having all these one individual wires wrapping around, if they're wrapped around so tightly together, it's as if you have a surface current density running through on the barrel of the cylinder. Okay, so if instead of telling you a solenoid, but it's a K on the surface of the cylinder, you know the results exactly the similar to how you do a solenoid. Surface density on the cylinder, Ampere's law will work. A toroid, so this is where your wires are wrapping around like this, and you will have a B kind of running through with restraint inside of this, the sort of the donut shape. This one, Ampere's law also works. We will have a tutorial on this particular type. Surface current on a flat sheet, yes, Ampere's law, we just did that. The one thing that's tempting to use Ampere's law is a loop, but don't use Ampere's law because it's not usable. It's not useful. We need to use Gill's law. Okay, because you cannot find a loop that B is everywhere constant on that loop, and also you cannot find a loop that B is everywhere parallel to the loop or perpendicular to the loop. So that's why Ampere's law cannot be used to find the B field for a loop. All right, so that's all for we have Ampere's law. So we are now shifting gears to do the last topic in chapter 5, which is magnetic vector potential. You're very familiar with the idea of a potential, right? So in electrostatics, we defined a potential V. Okay. The reason that we can define a scalar potential is because the curl of E is 0. Okay, so using math, because we know from math, the curl of a gradient is always 0. So because the curl of E is 0, we know E can be represented using the gradient of a scalar. So that's why we define a scalar potential V. Okay, so this becomes V. So similarly, we will do the same thing for magnetic field. We will be able to define a magnetic potential A to describe the B field. So which one of these Maxwell equations do you think will help us define the vector potential? Just like this Maxwell equations tell us we can find the scalar potential for E. Which of these Maxwell equations can tell us we can find the potential for B? I'm going to let you go ahead and vote. I'll give you a hint that again, there's a piece of math knowledge that you find somewhere or ask your math friend. They tell you the divergence of a curl is always 0. Previously, we know the curl of a gradient is always 0. They also tell you the divergence of the curl is always 0. So from that information, which one of these Maxwell equations do you think will help us? 10 more seconds, okay? 10 more seconds. Okay, let's close this, and I'm going to go ahead and show you the results. Okay, I'm glad that we choose mostly C and D's, because now we find a vector potential for the B field. So it has to be something related to the B field, right? A and B are about the E field, so that's not very useful. And also we're knowing that the something special should be something is equal to 0, because that is similar to the math knowledge we were given. So yes, the choice D is correct. Very good. That is the no magnetic monopoles law, right? So because this we know from math, this is we know from physics. We look at those two together, we realize, oh, it looks like B can always be represented using the curl of some vector, right? Because the divergence of the curl is always 0, pure from math. And the divergence of B is always 0. So you can represent B using a curl of some vector. And that vector is defined to be a vector potential. So B is the curl of the magnetic vector potential A. Just like how E is defined to be the gradient of a scalar potential V. Okay, so B is, so D is correct. All right, so B is the curl of A. A is vector potential for a magnetic field. Realizing there's a lot of freedom in choosing what your potential is, just like the potential for E field. We say, okay, we can set our reference point to be 0 and infinity. And here at this location, you can say that is 20 volts. But you don't have to. You can say, you can claim this point to be 40 volts, 55 volts, 100 volts, however you want, right? It all depends on adding a constant to it. And you keep your constant the same, just like you can call your gravitational potential energy to be 0 at the ground, or you can call it to be 0 at the table, depending on your reference point. So we have total freedom in choosing this potential vector potential A without changing the magnetic field. You can see that if you add a little constant to it, you can still, when you do the divergence of this A, you still get B. Without changing your magnetic field. And that's called the gauge freedom. You have freedom in choosing your potential, gauge freedom. But we are going to choose a particular gauge that is easy for us to do calculation. Is, yes, we have many choices for our A, but we are going to choose a particular A that the divergence of that potential is also 0, just so it's easy to calculate. Okay. And there is a proof in your book. We don't have time to do it in class. There's a proof in the book that this is always possible. It's always possible to find such a potential that the divergence of that potential is 0. So what happens if we choose this particular gauge that we call the Coulomb gauge? What will happen? So what happens is, okay, B is the curl of A. And in one of the Maxwell equations is the curl of B is mu naught J. That's Ampere's law, right? Current density give us B field. So now let's plug in B, replace B with the curl of A. So just previously, like we did, okay, del dot E is rho over epsilon naught, and E is a gradient of V. So we get Poisson equation, which is the Laplacian of V is negative rho of epsilon naught. This is Poisson equation. So we do the similar thing for the magnetic field. So you get, okay, the curl of a curl. You can check your book, and we found, okay, we know how to calculate this. This becomes gradient of a divergence minus the Laplacian of A. Okay. And now since we choose a Coulomb gauge, just for convenience, we can get rid of this first term. so that you end up with the differential equation that is the Laplacian of A is negative mu naught J. Okay. So giving any source distribution, so here, give any charge density, you can find your potential. Given any current density, you can find your potential. And further, you can find your B field from that potential. So here I claim that, okay, this is a differential equation for vectors. So which means I have 3 differential equations for each of the components, x direction, y direction, z direction. So if I simply look at the x direction, is the Laplacian of the ax component equals mu naught j, jx component. So I claim that I can right away know the solution to this equation. I know A, so it's going to be mu naught over 4 pi, the integral of j d tau over r, script r from the source to the field. So how do I know this? How can I write the solution to such a complicated differential equation right away? Is there any previous knowledge that can help us write down the solution to this new piece of information fairly quickly?
Uniqueness theorem?
I'm sorry?
The uniqueness theorem?
What is the theorem? I'm sorry, I did not hear.
The uniqueness theorem?
The uniqueness theorem. If you can guess the solution, yeah, that one. That one is like if you can guess the solution, then that's the only possible solution. But now my question is more, how do you even guess that solution, right? How do you even know what to guess? Okay, so I see a question, an answer in the chat says Poisson's equation. So this looks very much like a Poisson equation. Yes, each of the component is a Poisson equation. So I'm going to write this here. Mathematically, there's no difference between these 2 equations, right? It's a Laplacian of some quantity equals to a negative of some constant. So if we have solved this before, which means we can solve this new equation right away. This is rho d tau over script r. Now, which means this one is solved automatically. Let's not redo the work if we don't have to. So it's going to be constant times j. So instead of rho, we have j. Mu naught is also, I already moved it to the front. So it's going to be j d tau over script r. Okay, now you have ax, ay, az. So that's why you can add all of them together to be represented in the vector format. Okay, so again, you will see that we draw this analogy with knowledge we already know, and we save us a lot of time. So this is just like a Poisson equation, and we jump to our conclusion right away. We know how to solve this. So here is a little diagram you can find in your book. It's simply showing the relationship between J and A and B. Okay, so a lot of times if you're giving a current density, you want B, there are 2 methods. One is you integrate it, like the brutal force, you just go ahead and integrate and I can solve any problem you're given. But oftentimes complicated, that's the Biot-Savart. You can do this. This is a Biot-Savart law. Or when symmetry allows, you do Ampere's law. So the symmetry, I've already showed you all the problems that you can use Ampere's law for. So when it works, use Ampere's law to solve B. Okay, or sometimes you can find A first if it's easier. So you use the J, you use this equation to find A, this equation. Now this is a solution to the sort of the Poisson equivalent for this potential, right? And you can take the curl of A to find your B. That also works. Okay, so that's sort of the general idea behind the vector potential. Is like so it's very similar to the relationship we have in terms of rho, v, and e, right? Sometimes you just from rho to e you use direct integration, or you use Gauss's law from rho to v. We've done all chapter 3 is doing to the V first, and you take the gradient of V, you get your E. So it's again very similar, sort of like this triangle relationship. Okay, that being said, now let's see what how useful is this strategy. All right, again, a solenoid. We just solved a solenoid, so we should feel pretty comfortable with doing such a problem because we already know the solution. But we want to use a different approach. We want to find the vector potential because we know that if we do the vector potential first, and then we can do the B after taking the curl of the A. So after we got the A, we can simply do this to find the B. So given a solenoid, what do we do? Okay, let me add a page. So for the solenoid, okay, actually I'll take that back. In this case, we actually kind of have to already know something about the solenoid because the method I'm going to take will have to be based upon the assumption that we already know something about the B field of the solenoid. Sorry. So for that, I say, okay, for the solenoid, we already know B is constant inside. You may not know the exact format. You don't have to know the exact format, but you know that it's a constant inside and it's 0 outside. Okay. And you need to take the curl of this quantity you're trying to solve for, then that should give you the B result. Okay, again, I'm going to be lazy and say, I don't want to really solve this problem. I want to find a similar problem I've done before and copy the result. So I want to see, okay, mathematically, have I solved a similar problem before in the class? And I recall, oh, there is a totally different problem. The problem I solved is I was given a current density J that's uniform inside and is 0 outside. Okay, so you probably see this is what? This is a thick wire, right? A thick wire. So for a totally different problem, I have solved this problem before. Given a thick wire, I already know what B is because the curl of B is mu naught J. Okay. So I find the great similarity between these two problems. Mathematically, I know that, okay, I have already solved for this quantity and I already know the curl of this quantity gives me another quantity that's uniform inside and 0 outside. So can I use the result for B and write my result for A? Because mathematically, they're very similar. I need to find an A format so that the curl of A gives me a quantity that is uniform inside and 0 outside. Okay, so math-wise, these two equations, these two problems are not that different. So we're gonna do flip to our notes and we found, okay, we solved this problem. The B is mu naught JS over 2 phi hat inside. B is mu naught J A squared over 2S phi hat outside. Okay. So given that, can you go ahead and write your answer for A? So I give you a minute. Go ahead and try to write it on your piece of paper or your notes. Now can you go ahead and simply write your A quickly? You can see that exactly, you're allowed to use B naught Okay, B naught is equivalent to the J naught here. The only difference is here you have no mu naught. Here I have extra mu naught. So go ahead and write what A should be for the solenoid. Or if anybody have their answer or parts of the answer, feel free to let us know. Type in the chat or just talk about it. What do you think A would be for inside? Drawing analogy to this result. Anybody?
A S over 2.
Something over 2. B naught S over 2, right?
Yeah.
Excellent. That is exactly correct. J naught is a B naught here, and you don't have a mu naught, right? You don't have a mu naught, so there's no mu naught. So it's B naught S over 2, phi hat. Excellent. Now outside, mu naught is gone. J naught becomes B naught. A squared is still A squared over 2S. That's it. You can say, I've solved the problem. There you go. That's the answer. And that's perfectly fine. Okay, you can go ahead if you want to plug in your mu naught, replace this with mu naught and I, mu naught and I, and that's your final result. So A for a solenoid is mu naught and I S over 2, the phi hat inside, mu naught and I A squared over 2S phi hat or outside. See how quickly that we have solved the A, but in this case, I would have to admit that we already know our B, right? So getting our A is not really useful because you already know your B. But you can double check to see if that's indeed a correct vector potential by taking the curl of it. I'm not gonna have time to do all of it, but I'll write down the equation so you can check yourself. So curl of A is the A phi direction, the Z, sorry, in the S hat component, 1 over S d ds, S A phi over Z hat. So you can go back and check if you do this, do you indeed get your B field that you wanted to see if this is actually correct, okay? You can go ahead and check that later after class. The very interesting thing about this, you might wonder, well, does that mean you already know your B, so getting the A is kind of useless? Is A really just a math game that we play? It doesn't really carry any physical significance, so it's just, and we already said you can have all the different freedom in choosing the gauge freedom. So is A simply a math game that we play and it doesn't really tell you anything about the fields? And there have been different arguments historically in which one is more physical, E or B, or versus V versus A, right? So these are the fields, these are the potential. You know one, you know the other. And in a lot of ways, knowing either one of them is equivalent of knowing something else. But which one is more physical? And people might argue that, oh, this is more physical because these are the real fields and these are really just the potential, maybe just a math game. But later on, people have discovered in 1959 with two scientists with their initial A and B, and later on that their name are being carried over to talk about the AB effect, that you can have a non-zero A where B is 0. So it's possible for A to be non-zero, but B is 0. And if you argue B is more fundamental, then your particle should not be affected with a 0B. But however, for example, they did this experiment of having a solenoid here, right? So for we have the particle passing through the double slit. This is double slit experiment. So if the solenoid, this is outside of solenoid. Outside of solenoid has no B, right? Have zero magnetic field. So which means having this here should not really affect the path of your charge if you think B is more physical. However, you did notice a phase shift because you have a non-zero A. There is you can see a physical effect of the vector potential. So an argument of A is also physically a physical quantity. So this is named after Haronov and Bohm for the AB effect, but it's very interesting because the initial of the scientist is AB and also describing the relationship of A field and B, so it's called the AB effect. I just wanted to mention that briefly. Okay, all right, so let's continue to move ahead with A. Okay, so what else can we know about A? All right, so one thing about A is you can know the direction of A very quickly because like the equation we have previously, A is, let me go ahead and write it out. A is mu naught over 4 pi J d tau over script R. So you can see the direction of A is decided by the direction of J. So if I give you a current, a long current running in the Z direction, and ask you, what is the direction of A here? What would you say? Okay, I'll let you guys vote. Okay, 10 more seconds. Any last minute vote? Okay, if not, I'm gonna close this. Okay, very good. There is no really, there's no trick here. Your A is purely decided by the direction of your current. Current density, the same direction as your current, right? So it's in the positive Z hat direction. Okay, so A is correct. So I'm going to use this example to solve, to go ahead and do an example of how do we get the A for a current carrying wire, and hopefully we can find the curl of A to get the B field. So we solved the current carrying wire 2 ways already, Biot-Savart and Pierce law. And now the third way, we're gonna get the potential first and then do the B field. So this example is you have a long wire with I in the Z direction. Okay, so it's in the Z hat direction. Okay, I'm gonna do a slightly more nuanced version that I'm going to do a J that is I over pi a squared for if you have a thick wire. But if it's a long wire, you can see the idea follows. So if you have a thick wire, the current density is I over pi a squared, and we wanted to find A. And you can see that A x is mu naught over 4 pi jx d tau over r. Ay is the same jy over r. Az is the same as jz d tau over r. Okay, so that is from the vector equation. I break it down to 3 different components. So J, you can see, is in the z direction only. Your current is flowing in z. You don't have any x and y component. So you know that if we want to calculate ax is 0, y is 0, az is not 0. So now let's solve for az. Okay, this is coming from this solution. Sorry, approximate this. Okay. Again, I'm going to be lazy. I do not want to solve this. I want to find analogies. Okay. All right, so have I solved something similar before? Now remember there is a previous problem of okay, we have a long wire with a charge distribution lambda. And we know the E field for this. You have used Gauss's law to do this. So I'm going to recall the results. Actually, I'm going to write the results, the final results. Okay, lambda over 2 pi epsilon s. Right. And we're not really concerned about the direction here. We just want to borrow the results of the expression. So this is the E, and this is described by Poisson equation, obviously. Okay. And V is the integral of E dl, and I know the scalar potential. It's going to be negative lambda over 2 pi epsilon, the log of s, natural log of s. All right. Okay, so I'm going to be lazy and borrow the results as I have here. I want to draw the analogy between these 2 different situations. Okay, I see, okay, the Laplacian of something is negative with some constant, and the result is calculated by this. Okay. And I realized, okay, this is really not expressed using rho, so I want to express this using rho so that I will be able to write my expression for A. Okay, so the next little caveat that here is, okay, so I'm going to interpret rho to be lambda. So how do I do this? I know that in the volume of this much surface area times this much length. So in this volume, I have this much charge. And the same amount of charge can be described using lambda times L length. So I draw a relationship between rho and lambda so that I know that my lambda is rho pi a squared. So let me modify my results. I conclude that if you have a math equation like this, I know the result is negative rho pi a squared over 2 pi epsilon log s. So this is what we wanted to compare this one with. So look at these two, they have the exact same format, right? The difference is the constants. So I can carry over this result and write my A right away. So instead of writing rho over epsilon naught, all I do is replace rho over epsilon naught with mu naught j. It's mu naught j pi squared over 2 pi log s. And do some cancellation to simplify this. Final result will become AZ is mu naught. Sorry, I still have a negative sign. Negative mu naught JA squared over 2 log S. Okay. All right, so I did not have to do, the reason for this is in a lot of our problems, with A, you will be able to find a counter example you already solved in the electrostatics, and you simply apply the results without having to do the work again. So it saves you some time. And you realize J a you can write J pi a squared in terms of I. So another way to write this is mu naught I over 2 pi log S. That will be the same as Y. Okay. So if you have a density for a thick wire, you can do this. If you simply have a current, you just do this. Okay, so one last step. Will this give us the B that we were looking for? Okay, this becomes a dAz over ds in the phi hat direction. So this becomes mu naught I over 2 pi s in the phi hat direction. So if I plug this in here, look at this. This is indeed the correct expression for B for a long wire, right? And we got the same results by doing the A first. All right, so that's all for today. I know I walk you through the discussion for vector field fairly quickly. But again, I want to let you know the examples we do for A. Oftentimes, we try to draw the analogy from what we already solved before. So math-wise is nothing new. It's already been done. Okay, so Wednesday, there will be the midterm this afternoon from 3 to 4. I will be open up my office hour. If you have questions, feel free to come. Also on Wednesday, the same time for office hours, or at our regular class time, I'll open up our class Zoom, and you can come by if you have technical difficulties as well. Okay. All right. Have a good rest of the week. I'll see you on Wednesday. If not, I'll see you next on Friday for recitation.
Sounds good. Thank you, Dr. Ryan.
Thank you. Thank you. Bye.
I have a question, Dr. Ryan.
Yeah.
Would you? I didn't quite understand the analogy when you did the first analogy, the solenoid problem analogy, when you were finding A for that one. I didn't quite get the.
Oh, so mathematically, this is the same solution. So the solenoid is, we know, assume we already know B is constant inside, 0 outside. And we want to find a vector so that the curl of this vector describe this relationship of B. And the analogy is, well, we already solved B for a long wire, that the position of B is the same position as A. So the curl of the B is equal to a constant. The constant is exactly same as we are doing here. So I'm going to just use whatever B is, and that's going to be similar for my A. Does that make sense? So A is to B is how B is to J.
Oh, okay, I see that now.
Yeah. Okay.
Thank you.
Okay. Bye-bye.